Okie dokie. These are some exponential functions. Okay, so like it says, exponentials come up a lot on this AP test. You need to know, right, what they look like, their equations and such. So let's look at our exponential functions and some things you should know about your exponential function. Okay? One thing you should know is that they always have a horizontal asymptote. And unless there's been some type of a transformation, the horizontal asymptote goes through your x-axis. Okay, so that has the equation y equals 0. So every exponential graph has a horizontal asymptote. Okay, and if there's not a vertical shift, then the horizontal asymptote is through the x-axis, or y equals 0. Okay, as we're going to find in a second, they have an x-intercept. Your x-intercept is always going to be at the point 0, comma a. Okay, and we'll talk about what a is here shortly, but it always crosses, so you can always figure out what your x-intercept is from your equation. Right? This a term comes from your equation. Sometimes it's hiding, but it is definitely in there somewhere. Like we have 2 to the x. Okay, so we'll find out that all exponentials are a times b to the x power. Okay, so in this case, 2 represents your b value. Right, that's your base, or your common ratio. Right, what are we multiplying each term in our sequence by? So what would the a term be if we don't see one? That would be positive 1. Right, so they're there, they just don't always get seen. So if this were our graph, this would cross at the point 0, comma 1, because that's your a value. Okay, so also exponentials will always either have an infinity in them somewhere, and then they'll have a horizontal asymptote is what they express. So we'll go over some of these when we talk about limits in a minute. Okay, so here are some other things about exponential growth and exponential decay. So notice growth, if we have a b value, a base greater than 1, then we have exponential growth. And if we have a b value that's between 0 and 1, right, a fraction less than 1, because fractions can be greater than 1 also, like 5/2, that's greater than 1. But as long as your fraction is less than 1, then we have exponential decay. All right, so in our function, of course, a represents the initial amount, which, as we talked about, is your x-intercept. Right, that's your y-coordinate of your x-intercept is your a value. And b is your base, or your common ratio, our multiplying factor. Are we multiplying each x value by 2? Right? What is it that we are doing when we relate this to a sequence? And that's what we've done before, is relate this to a sequence. So our graphs are always either increasing or decreasing, right? So exponential growth is always increasing. Exponential decay is always decreasing, right? The y values. There are no local extrema, right? There's no mountains, there's no valleys, there's no changes. It's always either concave up or it's always concave down. Okay, over here. No points of inflection going on with our exponential graphs. Okay, it doesn't ever change from one to the other. All right, let's look and see what's going on the back side of our notes. Okay, writing limit statements, right? We've done that a lot in this course, and it's going to continue for every single function that we have. So remember, we have a left side limit statement and a right side. So we always start with the words lim, L-I-M. Right, underneath the word lim, we do our x approaches. And if it's the left, that means x is approaching negative infinity. Okay, and we'll call this function, let's call it f. So the limit of f equals, right? So like I said before, all exponentials have horizontal asymptotes. And as this graph is an exponential growth graph, if we go to the left side, that means our graph or our y values are approaching your horizontal asymptote, which in this case is going to be 0. So 0 is the horizontal asymptote that our graph is approaching on the left side of our x-axis. But what about the right side? The limit as x approaches positive infinity. Right? So when you're writing these limit statements, be very cognizant that all of this stuff is on the same line. Right? This is all on the same line, and the only thing that's beneath it is your x approaches, your x arrow infinity stuff. Okay, so just be careful when you're writing it that you're not putting things in places where they don't usually belong. Okay, so to the right side of our graph, as x approaches infinity, where are our y values going? Up to positive infinity. Right, so our answers for an exponential limit are either going to be a horizontal asymptote or it's going to be an infinity, either up to positive or down to negative. Okay? So here we have another example. Let's write our lim statements for the left and the right side. Okay, so on the left side of our graph, as x goes to minus infinity, our graph goes in what direction? Down, so it's going to negative infinity. Right? So this is a reflection of an exponential decay, right? That's been reflected across the y or the x-axis. Just so you know, we'll talk a lot about this in the future, but this is an exponential decay graph, right? That came from this, so this would be its reflection, which is why I know it's decay. And then on the right side, what is our y values trying to approach? 0, which is the horizontal asymptote for our graph. So we're either going to infinities or we're approaching a horizontal asymptote. Those are your options. Okay, part C. Is this an exponential growth graph or is this an exponential decay graph? This is, in fact, exponential decay, right? And it's called G, so we'll put a G in here. How do we know it's decay? The ratio is between 0 and 1, right? 2/3 is less than 1, so we know that this is an exponential decay graph that crosses our y-axis where? At positive 5, right? That's our y-intercept for our graph, positive 5. So we could do a little sketch, and we're going to do lots of graphs later, but we could do a sketch of this graph. It crosses your y-axis at positive 5 and is exponential decay, so it's going to approach 0, right? We don't ever get to 0, but 2/3 of 2/3 of 2/3 of 2/3 is getting smaller and smaller and smaller, so it's going towards 0. So on the left side of our graph, where is our arrow pointing? It's like it's up to infinity on the left and down to 0 on the right, because 0 is your horizontal asymptote, right? Because our graph has not been vertically shifted, we have a horizontal asymptote through 0, and your exponentials will never cross, but we'll always try to get there. Okay, so those are your two things. We either have infinities as your answer, or we have the horizontal asymptote, wherever that may be. Okay, so our next little section, is your graph concave up or down? And are the y values increasing or decreasing? Okay, so believe it or not, A is concave up. That's a concave up graph. And the y values are decreasing, right? They're getting smaller and smaller and smaller as x is getting larger and larger, right? As input values increase, y values are getting smaller, decreasing. Okay, part B, concave down. And are the y values increasing or decreasing?
Increasing.
The answer is decreasing. They are getting farther away from zero, getting more and more negative. So larger and larger negatives are decreasing values. Okay, if you think about your bank account, now you're going into debt. You're getting more and more and more debt, right? Which is your money, your value is decreasing if you have more and more and more debt. Now part C, is this a concave up or concave down? Probably an up, because this is an exponential growth graph. We have a base value that's 4. 4 is greater than 1. So this is concave up, and our y values are always increasing. Okay, so all increasing functions, all positive growth functions look like that. Concave up and increasing. Very good job. Okay, so our last thing is the tables. The first thing that we check in the tables is always our delta x. Right? In order for us to use a table to establish what type of a function this is, we need to have the same intervals. So 1 to 6 is plus 5. 6 to 11 is, okay. So that means that we definitely have equal length inputs values, right? Equal length. So they're all 5 units apart. So then because that's true, now we can look at our delta y's. So 3 to 5 is 2, and then 4, and then 8, and then 16. Right, so hopefully you know this is looks like a times 2 type of a business here. Of course, it's not exactly 2 because of our y values, but this will let us know that we have an exponential function because we have a multiplicative factor. Exponential, right? No, it's not linear, it's not quadratic. So it's exponential. Okay, so there's a little bit more about our exponential graphs, a little introduction to some graphs, and writing limit statements of our exponentials. And that is all. Have yourself a fantastic day.